Hello and welcome to the CompTIA Cybersecurity Analyst CySA Plus Certification Study Guide. In this video, we will discuss Chapter 5.1 Common Techniques for Investigating IOC. Please like, subscribe, and leave a comment. Hashing can be used to help determine if a file contains malware. Instead of spending hours or days examining the file's content, a message digest or hash of the file can be generated and compared with a list of digests created from files that have previously been identified as malware. Using hashing algorithms to generate message digests on malware helps to standardize and simplify the exchange of IOC among cybersecurity researchers. Common techniques for investigating IOC. There are several common techniques that cybersecurity professionals use to examine an exploited system when looking for IOC. Typical techniques include diagnosing malware, analyzing email, and examining user behavior analysis. How can a cybersecurity professional determine if a file contains malware? There are different techniques that can be used to identify malware. The two major techniques are to compare message digests and use file analysis techniques. Not all cryptographic algorithms are designed to create ciphertext that can later be decrypted back into plaintext. Some algorithms create output that cannot be reversed. One of these one-way cryptographic algorithms is a hash algorithm that creates a unique digital fingerprint of a set of data. This process is called hashing, and the resulting fingerprint is a digest, sometimes called a message digest or simply a hash, that represents the contents. Although hashing and checksums are similar in that they both create a value based on the contents of a file, hashing is not the same as creating a checksum. A checksum is intended to verify or check the integrity of data and identify data transmission errors, and a hash is designed to create a unique digital fingerprint of the data. There are several common hash algorithms. Table 5.1 illustrates the digest generated from several one-way hash algorithms of the word Sengage. Use file analysis techniques. If a message digest comparison does not yield results, the next step is to look for evidence of malware within the file, called file analysis. There are two common techniques used when analyzing a file. Dynamic file analysis. Dynamic file analysis executes the program and then observes its behavior. Special software called debuggers can be used to watch the behavior of the file on a step-by-step basis and also note the effects on the computer to determine if they are malicious. Special software called debuggers can be used to watch the behavior of the file on a step-by-step basis and also note the effects on the computer to determine if they are malicious. Static file analysis. Static file analysis is also called code analysis because it looks at the different code components of the file. Static file analysis does not execute the file, but instead studies each of its internal components to learn its intentions. Modern malware uses evasive techniques to attempt to defeat static file analysis, such as embedding syntactic code errors that will confuse attempts at analysis, but that will still allow the code to function. Modern malware uses evasive techniques to attempt to defeat static file analysis, such as embedding syntactic code errors that will confuse attempts at analysis, but that will still allow the code to function. Dynamic file analysis can be performed by monitoring commands, and static file analysis often relies on decomposing the contents of the file. Monitor commands. The basic technique for determining any malicious activity of a file is to monitor the actions of the file. This can be done by looking for evidence of operating system commands that the file initiates to perform a malicious activity. Because malware typically launches other processes, uncovering the commands to invoke these processes can help identify malware. This can be done by looking for evidence of operating system commands that the file initiates to perform a malicious activity. Because malware typically launches other processes, uncovering the commands to invoke these processes can help identify malware. On a Microsoft Windows computer, threat actors will often invoke one of two different native command line interfaces. The more powerful CLI is called PowerShell, while a more limited CLI is the Windows Command Shell. Although it has a limited feature set compared to PowerShell, the Windows Command Shell has the advantage that its commands can be invoked without starting a new identifiable process on the computer. Although it has a limited feature set compared to PowerShell, the Windows Command Shell has the advantage that its commands can be invoked without starting a new identifiable process on the computer. Typical Windows Command Shell operations used by threat actors are to bypass security controls, collect system information, execute files, and modify system settings. There are limitations to determining malicious behavior by focusing on file behavior. Many applications legitimately invoke other OS processes. This can make it difficult to identify a malicious spawned activity and often results in a high number of false positives. Many applications legitimately invoke other OS processes. In addition, malware may give their processes the same name as a legitimate process, such as the Local Security Authority Subsystem Service, or LSAS.x, to escape detection. Instead of watching for a single suspicious command, it is often better to monitor process relationships. That is there a legitimate reason an application would invoke a specific process, such as a network connection to an external domain? Another technique used when analyzing a file is to use static file analysis to look into the code of the file for evidence of malware. This involves examining the file structure, recognizing patterns, and identifying dynamic URLs. Viewing the internal structure of the file is an important starting point in decomposing a file to view its internal code. There are several sophisticated programs that can be used to examine the internal file structure. Figure 5.1 illustrates a program that exposes an internal file structure. Pattern recognition is the ability to detect arrangements of characters or data that can yield information. This can be done through examining strings, which are sequences of characters embedded within a file. Examining strings in a program can give clues about the program's functions. For example, if malware creates a file, then the file name of the new file is stored as a string within the malware. Strings extracted from a file can contain references to file names, uniform resource locators, URLs, domain names, Internet Protocol IP addresses, attack commands, Windows registry keys, and so on. An example of output from a string extractor program is shown in Figure 5.2. Although strings do not always provide evidence of the underlying purpose or capability of a file, strings can give a hint about what the malware is attempting to perform and is capable of doing. Because of the obvious telltale signs that strings can reveal, threat actors go to great lengths to mask their strings within programs. Techniques for masking strings include adding superfluous characters, caret symbols, commas, double quotes, parentheses, and semicolons, using coding techniques to create strings that are difficult to follow, such as embedded for loops, and creating environment variable substrings that are difficult to trace. Threat actors also mask strings to hide URLs linked to online remote devices through which the attackers send commands back to infected devices. These infected devices receive instructions through a remote online command and control (C&C) structure managed by attackers. There are several ways for this communication to occur: endpoints that sign into a third-party website, commands via blogs, specially coded attack commands through posts on X, formerly Twitter, or notes posted in Facebook, or a dead drop C&C mechanism used by creating a Google Gmail account. After creating the Gmail account, the C&C mechanism creates a draft email message that is never sent, but contains commands that the bot receives when it logs into Gmail and reads the draft. Because the email message is never sent, there is no record of it, and all Gmail transmissions are protected so that outsiders cannot view them. However, most often communication with a CNC involves the compromised device signing into a website that the threat actor operates. In the past, these CNC sites were hard-coded with a static URL string embedded in the malware. However, if this static URL string could be uncovered, it can be locally blocked to prevent any infected computers from communicating with the CNC, thus limiting the malware's impact. In addition, once the URL of the CNC is known, then technology companies and law enforcement agencies can petition a judge for permission to seize the domain and stop all communications. Today, threat actors have turned to adding code to malware to create dynamic CNC URLs. This technique uses a domain generation algorithm, DGA, to create the URLs. These techniques can range from basic to very sophisticated. An example of a basic DGA is to have part of the URL hard-coded while one element is dynamically generated. A threat actor may divide the URL into 4 parts, 3 of which are hard-coded strings within the malware, but one part is dynamically generated based on unique information extracted from the infected device. This information may, for example, be a combination of the physical address of the network interface, the domain name of the device, and the contents of a registry value machine GID, a unique identifier for each computer. An example of a basic DGA to generate a dynamic CNC URL domain is shown in Figure 5. 3. A more sophisticated DGA involves multiple steps and produces multiple potential CNC URLs, making it even harder to trace. The steps as illustrated in Figure 5. 4 are as follows. The threat actor embeds within the malware code a static value, such as a dictionary word or a predetermined string of numbers and letters. A link to a source that can generate a dynamic value, such as a trending X hashtag, the insignificant digits of a foreign exchange rate, and/or the current weather temperature in a specific city, a pseudo-random string generator, and a list of top-level domains, TLDs. At a predefined time, the DGA in the malware inputs the dynamic string and then uses it and the static string as input into the pseudo-random string generator to create a domain name. And then it selects at random a TLD to finally create a random domain. The threat actor, also knowing the DGA and all the values, is able to generate a list of domains just like the malware can. They then choose one domain and register it to serve as a link to the CNC. This registration occurs a short period of time, sometimes as little as 1 hour, before the malware generates its random domains. The malware attempts to connect to the first domain generated. None of these domains can be resolved through Domain Name System (DNS) queries by the malware except for the one domain that the threat actor has just registered. If the attempt succeeds, the malware has reached the correct URL CNC. If an attempt fails, the malware will then generate the next potential domain and attempt to reach it. This process continues until the malware is successful. The malware receives its instructions from the CNC that applies for a specific period of time, such as 24 hours. Once that time is over, the process starts again for the malware to generate new potential domains to receive its next instructions for the next period of time. Early uses of DGA generated as few as 250 domain names daily. More recent malware generates up to 50,000 domain names each day. Defending against DGA is very difficult due to the random generation of domain names. An alternative is to search for a reference to a dynamic link library that utilizes network functionality. For example, on a Microsoft Windows computer, searching for ws2_32.dll indicates that the malware uses the network. DGA has been called one of the most important innovations in malware in the past decade. If you find this video useful, please hit the like button, leave a comment, and subscribe to the channel. To see more videos like this, please click in the rectangle in the middle of your screen. To see other videos from this channel, please click the circle on the bottom right. Thanks for watching. We will see you on the next one.